Hello guys, this is CodeNCode and this is another lecture of this queries on tree course. And in this lecture we are going to see how Moore's algorithm can be applied, on path queries on trees. So before we continue, let me just show you real quick what are the problems that we will be solving and what kind of problems are there which you will be able to solve using Moore's algorithm. There are more problems that you can solve using Moore's algorithm. First, just let me show one or two problems that we will be solving during this course. So first problem is this one. I think is more easy. The problem is you are given a tree and each time also given a query of the form ABC, and each node in the tree is assigned a number from 0 to n. 0 to n, yeah. So you have to tell whether there exists a node. You are asked whether there exists a vertex on the path from A to B. Yeah, there is a path query from A to B. Is there any vertex on path from A to B such that the vertex is assigned a value C. The number that is assigned on that vertex is equals to C. So this is the query that we have to answer. I think all we have to print is find and not find, and this is I guess easier than this one. So this problem is count on tree. Second, the question is, again we are given a tree with n nodes and each edge I guess is assigned certain, okay, again each node is assigned certain value, and there are q queries. Each query is of the form uv, and how many different integers, yeah, each node is assigned certain weight, and in each query we have to tell on the path from u to v how many distinct weights are there. So how many different integers that represent weight on the node? Yeah, same question. So from the path u to v, we have to tell how many distinct weights are there. So these are the two problems that we will be solving in this course, and later maybe in the future I'll be posting some videos regarding related to Moore's algorithm on tree. There are much more harder problems than these. These are just to get you started so that you have an idea. You must start from certain easy problems so that you get an idea how this algorithm actually works, and then you can modify things according to yourself. Now one more thing, again, if you have any query regarding this course, any doubt, make sure you ask your question here on this article that I've created on discuss.codechef.com specifically for this course. So if you have any query or doubt, just ask here. The benefit, don't ask that in the comment section. The benefit of it is that it is possible that there are other people in the future who are watching this video have the same doubt that you are having. So if one doubt is cleared for a certain person, it may help others as well if that guy is also having the same doubt. So that guy can directly read from here. He can check, okay, whether someone has asked this question earlier or not. If this question has already been asked, then he can simply read it from here. So it is important you ask questions or doubts here instead of the comment section. So this was all before starting, so let's go and start. So now this is the tree. Each node is assigned certain value. For this lecture, for the sake of this lecture, this doesn't matter. This is the flattened tree. I run a DFS. This is starting time of each node, and this is the terminating time of each node. If you are some new guy starting to you just started watching this video, just make sure that you have watched previous videos from this same lecture, because I've explained the flattened tree, basically Euler tree technique, and starting and terminating time. So I'm not going to repeat all of this. I have run a DFS. Starting from this node, we have gone like this, and then this, and then this. So this is the starting time of each node, this is the terminating time of each node, this is the flattened tree. So each node is assigned certain weight. So suppose the query comes of the form AB, and you have to print the sum of weights of all vertices from node A to B on the path from node A to B. Okay, this is also an easy problem. So the question is how we can apply the same question, how we can solve this query using Mo's algorithm. Previously we have seen that how subtree queries are solved using Mo's algorithm. Now this time for the path query. Now suppose the query is of the form of AB, where A is node 2, B is node 4. So on the path from 2 to 4, the result should be 10 because 3 to 2 is 10, right? So now when there is a path query, there are two different kinds of path. First, when another node lies in the subtree of first node. First of all, A and B should be specific. Now A is the node which is having the least starting point. So we see node 2 is having starting time 2, node 4 is having starting time 4. So node 2 is clearly having smaller starting time. That is why node A must be 2. Okay, if the query was like 4 2, where A is equals to 4 and B is equals to 2, then we would swap them. So it is important that node A is having smaller time than node B, otherwise we have to write a if else condition. So make sure node A is having this, I would call the source, and this I would call destination. So source must be having smaller starting time than destination. So now there are two kinds of path queries. First, in which the destination lies in the subtree of source. So node 2 is source, node 4 is destination. So we see destination lies in the subtree of node 2, which is source. So this is one kind of query. There is another path query, for example 3 and 8. We see node 3 is having starting time 3, node 8 is having starting time 12. So of course node 3 is the source, node 8 is destination. Now we see destination doesn't lie in the subtree of source. We see in the subtree of source contains only node 4, not the destination. So there are two different kinds of path queries. First, in which the destination lies in the subtree of source, and second query in which the destination does not lie in the subtree of source. Okay, so first let's look at those query in which the destination lies in the subtree of source. So node 4 lies in the subtree of node 2. Question: how you would be able to determine whether node this is one kind of query or another? For that you can find LCA of both of them. If LCA is equals to A, then this is first kind of query in which destination lies in the subtree of source. Otherwise it is second kind of query. Again, if you have no idea about LCA, that is lowest common ancestor, just I have in the advanced graph theory lecture series, I guess, there are two graph theory courses. One of the courses I have explained, I guess, in advanced graph theory algorithms, I have explained how you can calculate LCA, that is lowest common ancestor. Now continue. Since this is first kind of query, the answer of this query is starting time of A to starting time of B. So starting time of 2 is here, starting time of 4 is here. So if you see 2 3 4, starting time of 2 to starting time of 4, these are all of the nodes 2 3 and 4. We see the path 2 3 and 4 contains all of the nodes which lie from path 2 to 4. So in the Mo's algorithm, L would become starting time of A and R would become starting time of B in the first kind of query. So we see there are 2 3 and 4. These are the nodes on the path from 2 to 4, from source to destination. Now let's see, is it that easy? Let's go for 2 to 5. Now 2 to 5, we see, okay, this should be even easier than the previous one. We should get two nodes 2 and 5 because the path from node 2 to 5 is 2 5, right? Now again, as explained, for first kind of query, L becomes starting time of A and R becomes starting time of B. So starting time of 2 is here, starting time of 5 is here. So the total number of nodes from starting time of A to starting time of B are these. But we see we expected only node 2 to 5, but this is what we get. We are getting 3 and 4 as well. But there is special thing about 3 and 4 here. And the special thing is that node 3 and node 4 are appearing exactly twice, while node 2 and node 5 are appearing exactly one times. Now node 2 and node 5, which actually form the path from node 2 to node 5, are appearing only one times. The other nodes which do not form the path from source to destination are appearing exactly two times. And that is actually true for all of the nodes which do not lie on the path from source to destination. All of the nodes which do not lie on the path from source to destination would appear exactly two times. Why is that so? Now see, this is the source and this is the destination. But while we were constructing this flattened tree, first we went from here to here, that is in this subtree, and then we went into this subtree. Now node 5 lies in this subtree, not in this subtree, but we went from node 2 to this subtree while we were running a DFS and while we were constructing this flattened tree. Now since this subtree does not contribute anything to our path, that is why when we entered into this subtree, we must leave this subtree to enter the subtree in which the destination node lies. We see destination node lies in this subtree, but we entered here before entering this subtree. So what would happen? We must, since we have entered this subtree, we must leave before entering the destination subtree, right? So since you entered and you must leave as well, that is why all of the nodes which do not lie on the path from source to destination would appear exactly two times, once when you enter here and second times when you leave it. That is why from starting time to A to terminating time of B, from starting time to A to starting time of B, all of the nodes which do not lie on the path from source to destination would appear exactly two times, and all of the nodes which actually lie on the path from source to destination would appear exactly one time. So now we see A is equals to 2 and B is equals to 8. This is again the example of first type of query in which destination lies in the subtree of source. Now we see before entering this subtree in which the destination lies, we went to this subtree and this subtree. So from starting time of A to starting time of B, we must have these nodes appearing exactly twice. So 3, 4 should appear exactly twice, 5, 6 should appear exactly twice, but the rest which actually form the path from source to destination would appear exactly once. So this summarizes first kind of query in which LC of A and B is equals to A. Why A? Because A is the A is the node in whose subtree node B lies, right? And so this will be LCA of these two as well. Now once we find actually okay, this is actually the first kind of query. For Moore's algorithm, L would become starting time of A, R would become starting time of B. Again, A should be the node which is having smaller starting time than B. Okay. Now let's go for the second type of query in which destination doesn't lie inside the subtree of source. Now see 3 and 8. We see node B, which is the node B, which is node 8, does not lie in the subtree of node 3. Okay, so again what we can do, we can make L of the Moore's algorithm, L pointer of the Moore's algorithm to be starting time of A and R pointer of Moore's algorithm to be starting time of B. But there is a problem. You see, when we take starting time of A, from starting time of A till the terminating time of A, all of the nodes that you see are the nodes of the subtree of that node. So if I explain you, for example, from starting time of 5 to terminating time of 5, like this, all of the nodes in between you see are the nodes which lie in the subtree of 5. So for 2 you see from starting time of 2 to terminating time of 2, all of the nodes you see in between are the nodes which lie in the subtree of 2, right? All of these nodes. So if you take from starting time of 3, all of the nodes from starting time of A to starting time of B, from starting time of 3 to terminating time of 3, all of the nodes you would see in between would be the nodes in the subtree of 3. And we know on the path from 3 to 8, that is in the second type of query, on the path from A to B, none of the nodes in the subtree of A would actually contribute to the path, right? Because the path from A to B would be of the form from A to LCA and B to LCA, A to LCA and LCA to B, okay? And we see A to LCA, the path from A to LCA would contain no element from subtree of A. So it is unnecessary to consider all of the node from starting time of A, or in other words, it is unnecessary to consider all of the node which lie in the subtree of A. So instead of setting L to be starting time of A, we would set L to be terminating time of A. Terminating type of A to starting time of node B. So from terminating time of node A to starting time of node B, you see these are the nodes. Again, the path from 3 to 8 consists of 3, 2, 7 and 8. 3, 7 and 8 are there. 5 and 6 is the subtree in which we entered, and this is not actually part of our solution. That is why the nodes 5 and 6 are appearing exactly twice. But there is a special thing, you see the LCA would not appear here, because LCA is the node in whose subtree 3A and B both lies, right? So from terminating time of A to starting time of B, LCA would not be present there. And this is your so first of all, before giving you an assignment, answer of the second type of query, L would be terminating time of A, not the starting time of A, because from starting time of A to terminating time of A, all of the nodes in between we see are the nodes which lie in the subtree of A, and those nodes we know for sure, for 100%, that those nodes do not contribute anything onto the path from A to B. That is why instead of setting L to be starting time of A, we would set L to be terminating time of A, and then of course R would be starting time of B. No change there. But there is a problem when you set L to be terminating time of A and R to be starting time of B. All of the nodes in between, you would see those nodes that appear twice do not lie on the path from A to B, and those nodes which appear exactly once lie on the path from A to B, but except the LCA. So this is your task. Tell me, this is kind of assignment. Tell me again, you have to tell here on the discuss.codeshift.com, the article that I've created for this course. So you have to tell why the LCA would never appear from starting time from terminating time of A to starting time of B. This is your task, and you have to tell. Just take some of the examples, and the answer you would find considering the flattened tree. So this is your task. This is you have to tell. So if I summarize the path query on Mo's algorithm, this would look something like this. First, we would construct a flattened tree. We would construct the starting array and terminating array. First thing done. Second, for each query of the form AB, first we would find the LCA. If A is equals to LCA, again A must be the node which is having smaller starting time. If that is not the case, simply swap A and B. So if LCA of A and B is equals to A, which means we are talking about the first kind of query, then query would be starting time of A to starting time of B. Otherwise, this is second kind of query, in which we will start from terminating time of A to starting time of B plus LCA, because LCA would not be there on from L to R in this range. LCA would not be there. Plus LCA means we have to add the solution of LCA separately. So this is how Mo's algorithm on path would look like. Next, I'll be taking an example problem so that the things will get clear. Again, you have an assignment. You have to tell why from terminating time of A to starting time of B, LCA of A and B would not be there. And this is for second type of query, not the first type of query. So this was all for this lecture. I hope you guys have some kind of maybe some doubts, or things were to some extent were clear to you. So if you have any doubts or query, of course go and put your doubts and query here and ask them here, not in the comment section, because not for all of the comments I get notification from YouTube. So it is a good idea to ask here, because for all of the notification, all of the comments that are made here, I get notification. So this was all for this lecture. Thank you guys for watching. Till the next video drops, keep coding. Thank you.